11 o'clock on a Monday. It must be organic. 6 weeks left, right? Starting to tick down towards the end of the term. A lot of stuff to come. Being organized is important here. And I'll talk again about imines and talk about some of the sort of controversy here about what actually happens forming imines. And I'll show you what I like to draw in terms of a mechanism. And hopefully at the end of the day, we'll be happy with nitrogen nucleophiles and carbonyls. And hopefully we'll be into maybe some carbon nucleophiles and carbonyls. So we left off on Friday trying to summarize this idea that nitrogen is more nucleophilic than oxygen. So these reactions work quite quickly. I reckon I'll get through 20 by the end of Wednesday, maybe. But I put the homework up there to be due on Saturday evening, and I'll put the quiz up there probably this afternoon to be due maybe Sunday evening. So you've got plenty of time to get into this stuff to make sure we're keeping up. Primary amines, secondary amines, you've got to be careful here. You've got to be on top of this stuff because a primary amine and a secondary amine are quite different, and they do different chemistry with different outcomes. Primary amines have one alkyl group attached or one R group attached. Secondary amines will have two, and the outcomes there will be very different in terms of where we go. So to get this started today, a very simple reaction here between benzaldehyde and methylamine. Where do you know methylamine from? Where have you heard methylamine on the TV? Breaking Bad? Yeah, it's one of the main ingredients when they steal that big train tanker. That's methylamine. Anyway, this stuff can be used in good purposes to be able to make imines. You can see here basically taking the amine, adding it to the electrophile, losing a molecule of water, and you end up with an imine. And as I mentioned on Friday, these are very useful in biochemistry to be able to join things together because we have this third valence. Water only has two valences, and so we can think about that forming ethers and things like that. But because this nitrogen has a third valence, you can link things together. So we'll see that a lot in biochemistry. I brought this slide in to sort of show you what we're doing in my other class and to maybe make you think about biochem. Imines are temporary linkers in biology. You'll see here that this compound is a conjugate between an amino acid and this pyridoxal phosphate compound in which the amine in the middle is temporarily holding those two pieces together. You'll then get some chemistry, in this case it's acid-base chemistry, tautomerism, stuff like that, elimination chemistry, and ultimately we want to get rid of that. So we'll see here that the imine can be broken down. We can hydrolyze it very much like we hydrolyze an acetal and go back to the carbonyl. In this case it's quite complicated. We have enzymes involved, biological catalysts, but it's basic organic chemistry. And again, this is the class I'm teaching in the spring of next year if you're interested, more mechanism. So when I talked about this on Friday, I said there's a bit of an issue in terms of how you write this mechanism. And if you notice, or if you're able to look at both the two editions of the textbook, he changes his mind. The author changes his mind from the first edition to the second edition. So what I did this morning was spend some time looking at all the textbooks on my shelves, which are many of them, and trying to find out if there's a unified sort of unanimous decision here in terms of what the mechanism is. And there really isn't. If you look on the website, the Michigan State website, which I have a lot of time for, the fellow uses the acid-catalyzed mechanism. If you look on some textbooks, they use the basic type mechanism. And the answer probably is somewhere in between. And this is all down to the fact that, unlike oxygen, nitrogen is much more nucleophilic. And so nitrogen is aggressive and goes after carbonyls, whereas in the acetal formation, you really have to protonate to make the reaction make it go faster. You have to protonate that compound to make it more electrophilic, and then the oxygen nucleophile gets involved. So there are two versions of this mechanism. I'm going to ask you to know this one, all right? And this one is on my website. I think you have this slide if you've been keeping a track of the slides. And it's just an interesting, idea that people are not quite happy with this in terms of teaching it. So the one in your book starts out like this. It starts out with a nucleophilic attack of the amine on the carbonyl, and you produce this species. And this species has a negative charge on the O. And that's pretty basic. And the problem with this reaction is that you're under acidic conditions. So producing that species is not going to live very long. And you can think now, what is the difference in these different steps? In the acetal formation, we protonated first, then we attacked. In this mechanism on the slide, we're attacking first, then we're protonating. It's the opposite. And you can argue as much as you want about how this works, but I'm going to suggest that you learn it in the same way we learned it for the acetals to keep everything unified. And in fact, if you go to the first edition of the textbook, I just copied this from the book at the bottom, he discusses exactly that. He says, well, we're trying to learn this stuff in a unified way, so it's not a whole bunch of different ideas. And in the first edition, he does what I do, which is protonate the carbonyl first, then we attack with the amine, and then we get the proton transfers. Ultimately, we lose a molecule of water, and we get the imine. And that fits everything else. That will fit the oxygen, the sulfur, and the nitrogen nucleophiles, and we'll stick with that in terms of the mechanism that you need to worry about. But the argument for why it's so complicated is because, number one, yes, nitrogen's more nucleophilic, so it should react faster with carbonyls than maybe oxygen does. but also if it's more nucleophilic, it tends to also be more basic. And the problem then is you have an acid in the presence of a base, and we can get into some problems here. We can run into some problems if we add too much acid, because the amine reacts with all the acid and you kill the amine, you kill the nucleophile. So in terms of a mechanism to get going today, we will protonate the carbonyl, we will attack with an amine, and then we'll do the proton transfer, and ultimately we'll lose a molecule of water and end up with the imine. Those steps are identical to the acetal steps until you get to this last part here. Once the water molecule leaves, this molecule is quite happy to go to the imine. You didn't get that double bond with the oxygen. You can imagine why, okay? In this case, we have that third valence, which is not a proton, and it's stuck there. You can't do that with an oxygen because it's only got two valences. So we ended up with the amine here, and that gives us a useful compound to do other stuff with. So again, this is what I'd like. If you're not happy with what I just said, go look on my mechanism page on my website. It's the same. Make sure you're okay with that. So in terms of utility, we can start to mix and match. We can start with different carbonyls, start with different amines, and end up with quite diverse products. So what you're looking for here in terms of a clue is the fact that each of these amines so far is primary. It has one alkyl group attached and two protons. And those two protons ultimately will become H2O, and we can lose H2O quite easily here. Down there, simple example, ethylamine, in this case some aldehyde, and again you're going to couple like so. Now there's a little bit more to this. You can imagine now this is a pi bond. And this is a pi bond with an R group over here and an R group over there. So if you have to discuss stereochemistry here, what does that look like? The R groups are on the opposite side of the double bond, so what does that look like? Trans, right? Trans. You can get cis and trans imines, where you can't do that with a carbonyl. So again, we have some interesting complexity here, some different diversity. Typically, you'll get the trans isomer favored over the cis isomer in that type of molecule. Down at the bottom, again, methylamine, and you've got the carbonyl here in cyclohexanone. Couple those two things together, get rid of the water, remove the water doing some sort of distillation, or, as was suggested the other day, put some drying agent in there, put some magnesium sulfate in there to mop up the water, and that pushes the equilibrium to the product. So imines are quite simple. They're quite simple to make. Now, the problem then is, again, running the reaction, in the sense of don't overdo it. If you dump in too much acid, you'll kill the reaction. And the answer to that, or the reason why, is very simple. The amine is not only nucleophilic, it is basic. And so it's looking to protonate. And if you find a strong acid around, you'll find that it will get protonated and it will give this. And this ammonium salt, which we'll see a lot more of later, this is not nucleophilic because the lone pair has been used up. There is no lone pair on that nitrogen now, and so we can't use it as a nucleophile, and so that's it, it's dead. So this graph at the top is just showing the effect of pH. If you're at very low pH, the reaction rate is pretty horrible. That means you've added a lot of acid, and everything got quenched. There's no nucleophile in there. And the ultimate, or the sort of best place to do this, or best pH to do this, is around 4 or 5. There's enough acid in there, it's still acidic, there's enough acid in there, but not too much. And again, you'll find that this is quite diverse and quite useful because you'll end up with a whole bunch of different imines just simply by swapping out the amine. So far, so good? Okay, right. More interesting, I think, and actually more useful to us as synthetic chemists, is something called an enamine. And the name of this is fairly straightforward. It's part alkene and part amine, and so we call it an enamine. And the change here is the fact that we have a secondary amine. We're starting out with a secondary system which has 2 of these R groups attached, and that gives you a different outcome. And the answer is because you don't have 2 protons. On the primary amines, you had 2 protons, so you can easily get H2O by deprotonations. You don't have that second proton here. So that second proton to make H2O must come from somewhere else. And ultimately, where it comes from is here. And once we're done with 20, and we get through to number 21, we're into a whole bunch of chemistry at this position. We call it the alpha carbon, next to a carbonyl. That will be 2 or 3 weeks worth of chemistry coming up. So those protons are acidic because of the fact that you have a carbonyl next door. And you'll see that, again, in general. Once you put a proton next to an electron withdrawing group, you can make it acidic even if it's on carbon. We haven't seen a lot of carbon acids yet, but we're about to. So the outcome here, enamine, the 2 R groups are intact. The double bond now can only be between this position here with the nitrogen and the alpha position, and that constitutes an enamine. Very easy to get these mixed up, so be careful. Now, how we do this, I'm going to suggest again that we protonate first, and we produce something like this, and then the mechanism is very similar to that for the amine. And you'll notice nucleophilic attack, all these proton transfers and what have you, and this last step, in fact, gives something that looks like an imine. The problem is that species now is not an imine, it's actually an ion. It's positively charged. We call it iminium. Okay, so this iminium ion here is not able to lose a proton like the imine was. The imine had an extra proton. It can come off quite easily in an acid-base reaction. So you could have gotten rid of one of these groups if it was a proton. You can't get rid of those two from an imine, right? They're stuck. Alkyl groups just don't break off like that. So what we need to do instead is to find a proton from someplace else. And if you look at this position now, the alpha position, you have hydrogens next door, which if you go after one, you can put the charge back onto the nitrogen. You can neutralize the nitrogen. And that constitutes putting a double bond next to the nitrogen. Now, any ideas what that mechanism looks like? You're starting out with a positive intermediate type species, and you have a base going after a proton, and you end up with a double bond. What was that? Intermediate carbocation attacking or being attacked by a base to give a double bond. E1, right? So go back and look at what the E1 was, and that should make some sense, right? It's very similar to an E1. So again, the story is you haven't got that second proton. It isn't going to be able to break off like it would for the imine, and so we get someplace else, and we go in a different direction, and we end up with an enamine. Now, enamines are all very useful to us as chemists because they react an awful lot like an enol, but they're more nucleophilic. Pierce? You can add Br2 to those things, I believe, yeah. Yeah, and in fact, they're more nucleophilic than regular double bonds because the nitrogen is going to push electrons in. So I have two different ideas now. I have this idea of forming imines and this idea of forming enamines. We are going to see now, again, if you swap the starting amine, in this case secondary, 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 you can get some quite diverse products. And again, we're linking things together. We're making bigger systems by simple functional group attack and linking things together. So in this case, what you're looking out for is, all right, there's my carbonyl. I know I'm losing water, so the oxygen must go. I end up with the cyclohexene system there, and whatever was attached to nitrogen is still there. The R groups are still attached. Here we've got this nice 5-membered ring, this pyrrolidine, and you can see now again that this would start off, we'd protonate over here, we'd attack with a nitrogen, and we get the same type of mechanism, and we'd end up with losing water from the proton coming up in the alpha position, and that then gives you the enamine. Down at the bottom, more elaborate again, cyclohexanone, this type of piperidine system, and again, enamines formed. So be very careful. They're somewhat similar to the oxygen nucleophiles, but you go different directions. It's up to you to keep a track of these things. Again, recitation, we'll practice these things and we'll talk about them in more detail, so you're happy with them. Now, in terms of, there's the argument from the textbook. Why does one go in one direction? Why does the other one go in a different direction? Simply because of the availability of a proton on nitrogen. If you don't have that proton, you can't eliminate from it. You can't take a proton off it. So in this case, what we're looking for here, to summarize, primary amines, secondary amines. Be able to identify one and the other. Primary amines have one group attached, secondary amines have two, and they go in different directions. And there's that proton that can come off from the primary system, and there's no proton there, so you can't take it off. So divergent pathways based on the absence or presence of a single proton. You want to slow me down here because 21 is impressive. So we can use this type of chemistry to do all sorts of different reactions. We can do all sorts of different things like reductions. This is called the Wolff-Kishner reduction. This is analogous to the Clemenson reduction when we take a carbonyl out of a benzylic system. You can take things like this. If you imagine the oxygen right here, we've seen this before. If you have an O in the presence of that NNH2 group, you can take it out by using zinc and HCl. That was the Clemenson reduction. And that turned a ketone on a benzene ring into an alkyl group. Well, that's happening under acidic conditions. And that's fine as long as there's nothing else in your molecule that is going to be attacked by acid. So you can see now as we build in, we have a quiz today and quiz this week, more elaborate type structures. As we're heading towards the end of the semester, we're thinking about adding things together in the terms of functional groups. We have to be comfortable with being careful. And in this case, there's nothing else attached on that benzene ring that's going to be destroyed by acid or base, so you could use either of these reactions, zinc HCl or this one which is using hydrazine. Now if you did have something over here that was acid sensitive, right, that you'd taken some time to make, you don't want to use acid, so you'd prefer to use base. And this reaction called the Wolff-Kishner takes care of that. You're going to use base, you're going to use potassium hydroxide and water after you've made what we call a hydrazone, and that's going to give you ultimately a alkane product. So you're reducing, you're taking out the C double bond N and ending up with two protons attached. Now mechanistically, this is a fun one, and I'm going to actually have you do this one because it's fun. So a hydrazone is the condensation product of a ketone or an aldehyde with this material, right? This material down here, NH2, NH2. Any idea what that's used for in technology? Ever seen this stuff before? Rocket fuel, right? You mix this stuff with oxygen and you get rockets up into space and what have you. It's an energetic system, and you end up with molecular nitrogen, which is very stable. So what we need to worry about this thing now is it's actually quite nucleophilic because I have a lone pair here repelling a lone pair over here. And so this thing is more nucleophilic than a regular amine. And what you'll do here is, again, the same type of reaction. If I had just used an R group here, the mechanism would give me an imine. If I swap that R group for an extra nitrogen, I get the same type of outcome. This is just an imine with an NH2 attached. Well, that's very useful to us because we can start doing some deprotonation chemistry and ultimately end up with a reduction. I have a carbonyl type system here. I have a methylene type system there. That's definitely been reduced. So in terms of how this works, you have to be careful and you have to heat it up in basic solution. So the mechanism for this is interesting. You start out with the hydrazone. Again, just make a note, mechanism is the same as it was for the imine. No different. And you think about this type of system. And now this is going to be not exactly the same, but it's indicative of what's to come in chapter 22 and onwards, is the use of carbon-based acids to do deprotonation chemistry. And we'll see now that this NH group is allowed to be deprotonated. What's the typical pK of NH as far as you're concerned so far? 38, wasn't it? It's quite high. They're not very strong acid. You have to use a very powerful base to deprotonate them. Well, now we're saying that we can use hydroxide. So that's got something, something different here. We're using hydroxide to take one of these protons off. And that's only possible if you can put the electrons somewhere good. And often that means putting them on an electronegative atom or delocalizing them. In this case, you can do both. So we can see two resonance structures. You can see now nitrogen, nitrogen, carbon, part of this 3-atom system, as we've seen for resonance many times. This is now negative charges instead of positive charges, but we did start out with negative charges way back when we did the acid-base chemistry. And we can see now delocalization between a nitrogen and a carbon. So which of those two resonance structures do you think is more significant, having more charge on N or more charge on C? More charge on N because it's more electronegative, but both of them will be somewhat basic and somewhat negative. So in reality, the anion here is shared between the two structures, the two pictures, and we can think about both of those materials, both of those atoms, N up here and C down here, being negative. Now, what's going to happen here, and the whole motivation for this reaction, is the formation of nitrogen gas, N2. Okay? N2 is almost about as stable as it gets. You have a triple bond here, and because it's a gas, it disappears, and it makes reactions reversible. It's a really, really powerful leaving group. So we're trying to get there. You can see here this structure at the top has an N double bond. I need to get an N triple bond. So I'm going to alkylate, or I should say I'm going to protonate on the carbon by a simple acid-base reaction to give this. There's the first hydrogen came in, right? Well, one of the hydrogens is now attached from the acid, and the acid happened to be water, and that gives you this species. Now, if you keep going with this, and you've got more hydroxide, you can go after that second proton. Now, that second proton isn't as acidic as the first one because I can't delocalize when I get to the anion. I'm stuck at this species here, but this is worth it. Even if this isn't that favorable, it's worth it because where we go next is the loss of that nitrogen gas. You can see now that pushing electrons in from the terminal nitrogen to make a triple bond here and forcing this bond to break right there, that's the problematic part of this reaction. Or it's also an indication of how good a leaving group nitrogen is. You're putting a negative charge onto a carbon like that. Is that a good thing or a bad thing? Bad, right? Bad. I mean, that's a pretty unstable, pretty reactive species. You want an indication of how reactive it is. What's the pK of the conjugate acid of that stuff approximately? 50, 60, depending upon which book you read. It's very, very, very weakly acidic. And so therefore, this is a super strong base. And you just made that species. The motivation to make it is to get rid of nitrogen gas, and that's an irreversible step, really. I'm not so happy that this is an irreversible error. I think that's not reversible. And you are able now to put the negative charge onto carbon, which isn't good. So carbon needs a proton pretty quickly. So we have some water around. We can deprotonate that pretty quickly, and then end up with this, which is an alkane. So the Wolff-Kitchener mechanism is, I think, interesting because we do some sort of logical things at the top, and then we kind of produce a species that we're not happy with. So it's not going to last very long. It's not going to sit around. It will get protonated pretty quickly. But overall, we end up with an alkane in which we have two hydrogens attached. So put this next to the old chemistry from chapter 19 with the Clemmensen reduction, zinc and HCl. You now have a basic version of that. So as we, again, get to molecules that are more complicated, we'll have to be careful. Do I need to use acid here? Do I need to use base? And you need to have the tools in the box to be able to do the right thing at the right time. Good one, this. Keep an eye on that one. Everybody all right? Pierce? Kyle? Chachko? Jaeger? Oob. All right, everybody's happy. Let's move on. So what we've done quickly here is we've sort of expanded our sort of toolkit by making imines, by making enamines, by making hydrozones. And a lot of those mechanisms were unified. They're very similar. There might be some divergent point at the end where an amine gives an amine gives an imine, or a secondary amine gives an enamine, stuff like that, but that's manageable. What you have to be very much aware of now, not just for my class, but as I showed you that slide just now, the biochemical ideas. Often nitrogen is linked in a temporary way. Often acetals are temporary intermediates. And we will use those as protecting groups when we do some synthesis. We can see here the acetal is blocked in terms of a carbonyl. It's taken the carbonyl out of the game, but maybe we need it back at some point. You've blocked it to take it out of a reaction, and then we need it back. So the opposite of the formation of the acetal, if you look at the mechanism, the opposite steps from the product to the starting material give you the ketone back, or the aldehyde. And it's completely analogous. You start out with, instead of the excess alcohol here, you're going to use excess water. We're going to have H3O+. And I did talk about this the other day, where you've got to be careful here. This is a complex reaction. This is not a simple quench. This is a complex reaction that involves hydrolysis. So what do you imagine the mechanism is for the first step? Proton, right? Protons protonate one of these things. If you protonate one of these things and you make the oxygen positive, what have you done there? What have you helped out? It's a better leaving group. So chances are we'll break off. And I'll show you the mechanism in a second. So if we're trying to keep this unified and trying to keep this all together so that we're not learning 10 different things 10 different ways, we can do the same thing with an imine. We can do the same thing with an enamine. Now these mechanisms you've actually seen before. You just haven't seen them with the same atoms. And as a part of the job as sort of becoming a better chemist, or maybe a biochemist, or whatever you want to be in the future, is starting to see connections and starting to see patterns that are revealing themselves. If you think about what needs to happen here, that molecule is certainly not the same as the one above it. This imine is not the same as the material above it. But what do you think the first step is in the hydrolysis? Protonate. Form a resonance stabilized cation. Go after it with water, form a carbonylamine type intermediate, and then lose a molecule of amine, and eventually you get the carbonyl back. And then down here, a little bit different, but I would imagine anybody who's getting anything out of this should be able to start this off quite quickly. I have two places to put a proton. I can put it on the N, or where else? Where else is a good place for a proton to go on that molecule? The alkene. Now, if I do this, because guess what? I need that proton because I have CH2 right here, and I have CH3 right there. I need a proton. So let's pick it up at that position. If I do that, I put the positive charge here. Is that a good thing or a bad thing? It's fine. Why is it good? Next to N, which has a lone pair, which can help out. Now, what is that? That's a rule from the first semester. You added a proton to a double bond in a regiochemical way that gave you the better carbocation. What's that called? Say again? That is Markovnikov. That is just a Markovnikov addition. Get a carbocation, stabilize it, and away we go. So these are simple ideas that you've seen. We're just putting them into different scenarios. So here we go. To hydrolyze an acetal, if you've been working over the weekend thinking about a quiz coming up and you've learned this mechanism for the acetals, it's exactly the opposite. And you always get somebody on the next exam who will say, I know the mechanism for forming the acetal, I just don't know the mechanism for hydrolyzing it. So I'm going to draw everything out in the forward direction, and I'm going to ask you to read backwards when you grade my test. I don't mind that. It's actually quite clever. Right? But you've got to notice now that this is exactly the opposite of what we just did. And that's the idea of an equilibrium. All the forward steps must mirror the opposite steps. So in this case, I have an acetal. I've used it as a protecting group. I've blocked something. I've done some chemistry someplace else. I want to get my carbonyl back. And ultimately, if I mix this stuff with water and acid, I get my ketone back. Stepwise, straightforward. And again, if you understand mechanism and starting to get something out of this, this will not be a lot of effort to learn. I'm going to protonate. Okay, got some acid around. I've got a catalytic amount of acid. I'll protonate. I'll produce this species. Now, again, I'm not that big of a fan of this type of picture. I like to see the extra resonance structure because I think it really helps us understand why this system got more reactive. And you think about what's happening here. The oxygen wants its lone pair back. So if I draw this resonance structure with a positive charge on carbon, the oxygen gets its lone pair back. But in reality, the system's somewhere in between. So you have a delta positive O and a delta positive C. And you think about the different situations here. This positive O has 8 electrons. This positive O only has 6. That's why the nucleophile will go after carbon, not oxygen. Oxygen's missing electrons. So in that second step, that's exactly what happened. The water went after the carbonyl carbon. I could use that arrow as well if I want to. It's the same thing. And that gives me this. So what I've done so far is swap out one of the OR groups with an OH group. I need to go further because the outcome is a ketone. So after that, we get a proton transfer, which you're quite welcome to just write as proton transfer. All that's happening here is a proton is jumping from there to here. That's this molecule down there. You then set up a leaving group on the second oxygen, on the OR group, and then it can break off in a reversible step and give this. And that's simply a protonated carbonyl. Now, unlike the imines, we do have, or the enamines, we do have that extra proton available to take off. We can go after it with the base, and that gives us the ketone. But importantly, what is the byproduct of that step? H3O plus, the acid, which can go back and react again. You can recycle and go again. So that is nothing too tricky. That's just the same we did last week. You've just got to be on your toes and recognize that I'm trying to help you learn this stuff in an efficient manner by not learning things twice. So you know it in the forward direction, you also know it in the reverse direction. We'll see that in restation a lot when we start doing protecting group chemistry, and I'll be talking about blocking a lot. Go on, Michael. Yes, I'm fine with that. Yeah. Again, the proton transfer is kind of counterintuitive because we've been so pedantic about this stuff for a semester and a half where you can't miss anything out. Now we're saying, okay, miss it out. And the answer again is biochemistry. The answer is always biochemistry. Right? It's a massive subject that contains many, many proton transfers, and you don't have time to actually do anything with them. So there's my hydrolysis of an acetal, and I would imagine you can go ahead and do that. I don't think I have the mechanisms on the slides here, but I would challenge you to have a go at the mechanism for this one and be happy with them. And if you want to do them and check them and ask me in recitation or ask me in office hours, do so. You'll find yourself, I think, gratified because if you know what you're doing, it's a piece of cake. If you don't, it's a nightmare. Okay, but this is indicative of where we are. Now, other types of systems we can use, thioacetals. If you can do the oxygen system, you can do the sulfur system. In this example, we're simply going to make them and use them. Mechanistically, asterisk, this is the same as an oxygen acetal. You're just swapping sulfur out for oxygen. Now, sulfur is below oxygen in the periodic table, so it has very similar properties. It has 2 lone pairs, so it's nucleophilic. It's bigger, it's less electronegative, and so it's easier to share its electrons. It's actually more nucleophilic. And it stinks. Right? This stuff is disgusting. The sample or the example of a thiol that you'll be familiar with is this one. And this is butane thiol. And if you're in Gen Chem Lab and you've got the Bunsen burners going and somebody's not lit it and you can smell gas, you're not smelling gas because gas has no odor. You're smelling this stuff. Right? This is put in as a deterrent or a sort of a marker. Hey, somebody's got the gas turned on. Because you're smelling this stuff and you know this stuff when you smell it. Apparently also if you run over skunks and things like that, they're full of thiols and they stink apparently. So here we go. We need an excess of the thiol and we need a ketone again and we get what's called a thioacetal. Thio is a prefix of sulfur. It's an acetal very much like the oxygen systems were. So let's just call it a thioacetal. Now these again have lots of utility. We do use them as protecting groups in advanced synthesis. Mechanistically you should be able to do that without me showing you. We're at that point now where I say, okay, the mechanism you know, go look it up. And we can do that again with the cyclic system, like we did for oxygen. The advantage of this system down here is that both nucleophiles are contained within the same molecule, so you get these fast intramolecular reactions, and you don't have to worry about intermolecular systems. So again, acid catalyst, protonate over here, go after it with a sulfur nucleophile, transfer a proton, lose a molecule of water, trap, and you get the product. So the products here are very useful. I made a bunch of these things when I was in Washington, D.C. They stink. You're not very popular when you do it, but they're very useful. And the biggest use we will see for these things is getting rid of a carbonyl. Let me put that in context. What we just did with the Wolff-Kishner reduction a few slides ago, this one right here, is we took what used to be a carbonyl right there, and we took out the carbonyl and replaced it with 2 hydrogens under basic conditions. Well, now we can do this with systems that don't necessarily have a benzene ring in there. This is useful for all sorts of different things. And you can take one of these dithioacetals and something called radionickel. Radionickel is fun stuff. And you get the same outcome. Mechanism for this is way beyond the scope of where we are here. Right? This is a radical anion type mechanism. It's horrible. But radionickel's fun because you've got to be careful when you do this. If you try to filter it off and you use a filter paper like you do in lab, you can get fires because this stuff is pyrophoric and it reacts with the paper and sets it alight. I've done that. You don't do it twice. So radionickel is a slurry. It comes in water. or ethanol, and it's just a metal which is coated with hydrogen. It's sort of infused with hydrogen, and it does this reaction very nicely. And it's a very elegant, very simple way of going from a carbonyl down to a CH2 group. And as we work our way into the later chapters, and we talk about things like lipids, where you don't have any functional groups, I want to put some context in. When organic chemists make molecules, you absolutely have to have functional groups, because alkanes don't react with alkanes. But what at the end of the day, your molecule doesn't have any functional groups? You've used the functional groups to knit everything together, but then you have to get rid of them. This is a great way of getting rid of a carbonyl and going back down to the alkane. So you can use that carbonyl in the synthesis and then get rid of it. So we'll see now, no mechanism required here, but a very elegant way of going down in very high yield to an alkane. Michael? It does react with other things, but I'm not so sure we've covered them. Yeah, we'll use it just for this one particular reaction. Okay. All right, so the bottom is a sequence. The bottom is a sequence where you take your carbonyl. Now, this has got nothing to do with the thioacetal itself. The thioacetal is just an intermediate. We're not making it for its own purpose. We're making it to go someplace else. And you will make that through the mechanism described for the oxygen acetals, and then you'll put this stuff in. So now we have a powerful reducing agent that will take this carbonyl, carbon, at the +2 oxidation state, and knock it down to that, which is a -2 oxidation state. Very useful. Keep an eye on that one, make a note of it. To summarize some of the things from earlier, so I can get into carbon nucleophiles, which is the beginning of the end for everybody, or the beginning of the beginning. Small stuff. You've seen this before. And we can talk about the uses of these two different reagents to reduce things. We have LAH and we have sodium borohydride. Which is more powerful? LAH. What's the argument behind that? Anybody remember? Electronegativity differences. There's a bigger electronegativity difference between Al and H than there is between B and H. And so we end up with this horrible dipole situation where hydrogen is very negative in LAH. And so it wants to react, therefore it's powerfully nucleophilic, but also basic. You put this stuff in the presence of water, it will fizz because it's deprotonating the water and giving you hydrogen gas. So at the bottom, I have sort of a mechanism that covers the LAH, but it's also similar to the sodium borohydride. You have a central Al or B, and you have a hydrogen attached to it, and those hydrogens are, unfortunately, carrying the negative charge because the central atom is weakly electronegative. So this is behaving as a nucleophile. We've often thought of these things as being H-, and we can use that to introduce exactly that. So in this case, we have a carbonyl at the top. We have either of these two sets of reagents, and we end up with, if I put the proton in there, we end up in this case with a secondary alcohol that came from a ketone. This will be useful. This will be powerful, because we'll do synthesis in the near future where you have to bounce around between aldehydes and ketones and carboxylic acids and alcohols and ethers and all those different things. We've done some of this before. We'll do a lot more of it. So mechanistically, we need two steps here. The answer to why you need two steps at the top is because LAH is so basic. You can't use this reaction, do this reaction in a polar protic solvent. It will quench the reactant. So we get the first step is nucleophilic attack, and the second step is a quench. And in this case, we're using water. You could use acid if you like, and we get the product. So you've seen that. Straightforward nucleophilic addition. We've also seen Grignards. Did everybody get the Grignard to work? Did everybody get Pepto? Yeah, hopefully. Okay, good. Again, I think the whole point of that reaction is to learn how careful you have to be, because they set it up to the point where don't fail this one. This is one that you want to get to work. You have to keep everything dry. You have to give your glassware in to get it in the oven to keep it dry. And the answer is fairly simple, because you don't want this reagent in the presence of any moisture, or else it will protonate and it will quench and you'll kill it. So what we'll get here is, again, nucleophilic attack, exemplified by this mechanism at the bottom. R-, again, I'm not a big fan of just writing naked R- like that, because I'm pretty sure it isn't R- like that. It's delta- from the carbon, delta positive from the magnesium, and the bond electrons from the C-Mg bond go after the carbon, and we do that. And that's nucleophilic addition. It is a very, very useful way of making carbon-carbon bonds. After that, you've got a quench to get rid of the alkoxide and end up with the alcohol. And this is good because you can now elaborate the molecule quite easily. You can start out with a lesser substituted material like an aldehyde and end up with a tertiary or secondary alcohol. You can start to add pieces together in quite a powerful way. And we did this a lot before the break in recitation, where we started talking about disconnections and talking about planning. That will come back again to be able to put these types of systems together. So we've seen that. We're trying to move now into carbon nucleophiles. This is mostly the end of this chapter. This type of sequence, it should not be anything different, anything new from what you've seen already. we can take the metal, again, just to make sure we're happy with this. In recitation, I've been saying this. Our author doesn't like lithium. Our old authors like lithium. So maybe our new author has shares in magnesium, but not with lithium. And he doesn't use lithium. But on lots of my old problem sets from generations past, you see lithium all over the place. If you see lithium, you think magnesium. Same deal. It's an organometallic, which will make carbon nucleophilic. So in this case, I'm using magnesium in the Grignard system. We're going to put the magnesium here, insert it. We're going to make a powerful nucleophile. This is a ketone, so we're going to do addition to it. And the motivation behind that, again, is you have a powerful carbon nucleophile. It's powerful because carbon doesn't want to be negative yet. In these systems, there's no electron withdrawing group, so carbon can't really bear that negative charge too well. So it tries to react with something else to get rid of its negative charge and transfer it onto O. That's the whole motivation of that process. O is much more electronegative, much better with a charge. After that, we quench, and you have a nice system. You have a nice approach to a more elaborate alcohol. So you can do that with aldehydes and ketones. We are working towards 37 steps. I'm going to bring that in probably on Friday and start talking about that 37-step synthesis. If you can do that, you're in good shape. Now, this is a reaction that people are still not quite happy with this. Okay, there are people out there on their internet still arguing about this stuff on blogs. Okay, people just don't like this reaction. It's the reaction between cyanide and a ketone. It actually has some use. You can take these types of systems and later on, in fact, no, maybe we'll do it later on, you can actually use this to make amino acids. Amino acids obviously have lots of use in biochemistry. So this product here is a cyanohydrin. Cyano, obviously, hydrin for the OH group. And the problem with this reaction is the pK of this and also this interpretation of it being in equilibrium. But it does start you off thinking about expanding the sort of playing field in terms of types of reactions. What's going to happen here is that you have a mixture of HCN and cyanide. So this is sodium cyanide or potassium cyanide, the deadly stuff. And it's a powerful nucleophile. We saw that in the SN2 chemistry. We saw that a while back. CN- is a very powerful nucleophile. It's got a negative charge on a carbon, and it's also very compact. It's sp hybridized, which isn't so bad because we can put the negative charge there, but because it's so compact, you can get places. So what's going to happen here to get to the cyanohydrin is straightforward nucleophilic addition, just like we did for a Grignard. But different to a Grignard here is that we have some acid around when we need it. In the Grignard, you have to add the acid in the second step to quench. This has the acid in there from the beginning. And when we get to this species, which looks an awful lot like the alkoxides on the previous slide, we can protonate it using HCN. But interestingly, what that gives you, not only is this product, but it gives you CN- back. And so CN- can go back and react again. So it recycles. But what you need to be aware of is that simply taking HCN, and I'd probably give you a clue as well, it'd be a mixture of HCN and NaCN, something like that, so you know you've got some nucleophile in there, and you get the addition product. They do have some use, but not as useful as what's about to happen. Everybody's very quiet today. Serious game. Okay, fair enough. There's the, in fact, he's actually put that condition in there. There's KCN with HCN, that's the clue. You have the nucleophile, you have the acid, you can go ahead and get the cyanohydrin. And you can get the same sort of system on a benzaldehyde, and again, you get the cyanohydrin here. There's some useful things later on, maybe I'll bring this in later. Some animals and plants actually use this type of product as a defense system. And they have the reverse reaction in which some trigger sets this off, where the carbonyl reforms and cyanide comes out. Okay, and that's a poison. So you can generate this stuff as a poison. It's an interesting biochemical system. But right now you're interested in the forward direction in terms of forming cyanohydrins. And it's just to get us ready for what's to happen next, because carbon nucleophiles are about to get really interesting. So once you've got these cyano groups, I'm not that bothered about this just now because we'll see it again in chapter 21 later. You can take that triple bond and get rid of it and turn it into an amine. That could be useful. And you can also hydrolyze these things to a carboxylic acid. You will see that in 21 anyway. So I'm not that interested in that. It won't show up on a quiz. It won't show up on a homework. But just be aware that these things now are sort of entries to other different functional groups. What I really want to get to is this. This is my favorite reaction since my last favorite reaction. They're all my favorites. This one you will grow to love. You'll remember this for the rest of your lives. You'll tell your grandchildren about this one. The Wittig reaction. Now, Piers, have you been practicing methylbenzene? What's methylbenzene called? Yes, what's the name for methylbenzene? toluene. Thank you, not toluene. Toluene. Now, Wittig was a German, okay? The Germans speak different. So his name is Wittig, not Wittig, right? Wittig. And the Wittig reaction is an incredibly powerful process for making alkenes. And this is the go-to system for making alkenes because your alkene goes where you want it to go. When you did the formation of alkenes, let's say by acid catalyzed processes, you've got carbocations, you might get rearrangements, you end up with a Zaitsev type outcome. You get more highly substituted double bonds as opposed to lesser substituted double bonds. What if you want your double bond to be the lesser substituted one, and you want it in high yield? Well, then you turn to Professor Wittig's chemistry, and this system will put that double bond where you want it in your molecule. It's fantastic stuff. Now, to get there, we need to make something called an ylide. I've got 10 minutes. I'm not going to get through all of this, but we're going to start doing some synthesis with this stuff. It's a mechanism that you will really enjoy because it involves really weird things. 4-membered rings, we don't like those. We'll get rid of it. And then we'll start using it in synthesis, and then Wednesday I'll finish up that chapter and be into 21. So we really are getting along now. What you need to do a Wittig reaction is a Wittig salt, produced by Professor Wittig. And we start off with this. This is a phosphine. And phosphines are fun. They are nucleophilic. They are the equivalent of a nitrogen. They're equivalent of an amine. In fact, this looks like a tertiary amine where I swapped out N for P. P is one below nitrogen. It's bigger, so it should be more nucleophilic. It is. And we can use it in a simple system to attack alkyl groups. Now, this is somewhat limited to secondary and primary systems. It's completely useless for tertiary systems. You'll see why in a minute. But if you have a primary system or a methyl group, you can go after that and do this type of chemistry. And you attack this because it's a lone pair going after delta positive, and you boot that out. What mechanism is that? SN2, my other favorite. Okay? SN2, that's all it is. Nucleophile going after electrophile, kicking out leaving group. Now, if you run this reaction in the appropriate solvent, it's really, really fun to do because if you do this in, let's say, ether, ether's polar aprotic, but the product you are making is a salt, and that's a salt which is charged, and maybe it doesn't dissolve in ether. And so what tends to happen here is it precipitates. And as the reaction is progressing, you see a solid form. And it's falling out of solution, and that's the salt. And that then can be filtered, and away we go. The outcome here, we have an alkylated phosphine. I believe it's called down here, there's the word, phosphonium salt. And that phosphonium salt, you can buy these things, or you can make them quite easily. They're quite stable. And we now are entering a very different world. We are now about to make carbon acidic. We're about to make things nucleophilic on carbon by deprotonating it, and that's been difficult so far. The typical pK of a CH bond has been a 50 or 60. There were some strange ones. Cyclopentadiene, 5-membered ring, 2 double bonds, had a pK of 16. Because when you take the proton off, it becomes the base becomes aromatic. Yeah, that's the one everybody missed on the exam, apart from the people who got 100. But, no, it was on the quiz, wasn't it? A lot of people missed out on the quiz. This proton next to this phosphorus is now acidic. And I want to do this so that when we get into 22 next week, the end of next week, we're not lost. This proton is all of a sudden acidic. And it's acidic because next door is an electron withdrawing group. So you're going to think of the phosphorus, because it's positive, as being electron withdrawing. And if it's electron withdrawing, it enhances the acidity of what's nearby. And it helps stabilize the negative charge if you were to put a negative charge next to it. Well, phosphorus here is a little bit, it's interesting because of the size of the thing. What we're going to say here is that one of these protons can come off. So if I just expand this a little bit and put the proton there, and I have a strong base around, I can go after that, and I can deprotonate. And I can put a charge onto carbon. You've got to be awake on this one. We're going to draw what's called an ylide. And an ylide is typically formed between atoms as neighbors that are different sizes. That's the typical type of system. You will see others later when you do some biochemistry, but this is typical of what you see now. The two atoms, the neighboring atoms, phosphorus and carbon, are right next to each other. And what you should be thinking is, well, this has a positive charge and missing electrons, and this has a negative charge and it's got too many electrons, so why not just get together and share and form a double bond? And that's represented in this second structure. But the problem is, you have a very large phosphorus trying to communicate with a much smaller carbon. Whenever that happens, the overlap between the orbitals isn't very good. It's not complete. So because we have this incomplete overlap and this sort of incompatibility in their sizes, we have to draw two resonance structures to describe the actual structure. At the very least, what this molecule is a very negative carbon. Even if you draw this structure over here, that carbon at the end is very negative, even if it's part of a pi bond. More electronegative than the phosphorus, and it's going to be nucleophilic. So you'll have to draw it either as this, or both, if we're asking for resonance structures. And you can use either of those to do what comes next. And what comes next is the Wittig reaction to make an alkene from a carbonyl. This is something, again, that's important that you'll remember forever. So here we go. There's the actual product of this reaction. You start out with the ketone. You react it with the Wittig ylide, which you've just made, as I've shown you. Again, practice this in recitation. And you swap out oxygen for carbon. Now, this is the simplest example of what we call a metathesis reaction. Not metastasis, that's different, metathesis. And this was Nobel Prize winning stuff a couple of years ago, not for Wittig chemistry, but something closely related to it. The idea that we are swapping groups. We are swapping this group and this group. And this piece over here will end up on the phosphorus, and this piece over here will end up on the carbon. You're simply swapping the two pieces. And we're going to see a mechanism now in which you get two pieces coming together, like a 2 plus 2, in this way, and then they break in this way. So it comes together to give a cycle, and it breaks in a different way. That's how you get the transfer happening. There's the ylide. There are the resonance structures describing the fact that this isn't a perfect double bond. It's very polarized, and it's best, I think, drawn like this so you can see the negative charge on carbon. See why it's so nucleophilic. And the mechanism for this is, I think the best word to describe this is glorious. It's just glorious. Every pre-med on the planet loves this mechanism. I have an alkyl halide from my website. I have a phosphine, typically PPH3. It's cheap. It's easy. Not easy to work with, but it's cheap. We get initial SN2 reaction between those two pieces. We form a salt. The second step is a base. THF is a solvent. We know that butyl lithium is a powerful base, so that will be used to deprotonate. And then the carbonyl is going to give us the outcome. I'm going to do this now with my last couple of minutes, and I'm going to do it again on Wednesday. There's your initial salt formation, SN2 chemistry. Everybody here should be able to do that. That enhances the acidity of the proton next door. The positive phosphorus is pulling electron density away from the proton. You need a powerful base here. Butyl lithium is good. Go after that proton and take it off and produce the ylide. This isn't usually stable. You can buy stabilized ylides, but most people will make them themselves because they degrade over time. And you'll do this in a flask which is dry, in a solvent such as THF, which is dry, because the bases would react with water otherwise, and you'll produce your ylide. Now, your ylide here, if you want to put it all together, your ylide is the nucleophile. Whereas previously we used amines or alcohols or thiols as nucleophiles, this is your nucleophile. But it also gets into later chemistry where we have now stabilized the negative charge by putting it next to an electron withdrawing group on carbon. So this thing is nucleophilic. It will want to go after that carbonyl carbon. That's exactly what will happen, like so. That step there is simply nucleophilic addition. Nothing more fancy than that. That gives us this stuff, which now has a possibility for closing a cycle. You have a positive O. No, you don't. You have a positive phosphorus and a negative O. And they're going to talk to each other because there is a strong affinity for those two elements. That closes to give us this, which is horrific. It's a 4-membered ring with a phosphorus, which is not going to last very long, and that breaks apart and gives us that. So I'm going to stop there. You give it a look over the next couple of days, and we'll do it again on Wednesday. All right, see you in recitation in about 10 minutes.